Hello and welcome. If you found your way here tonight, maybe you're looking for something gentle, something quiet, a place where curiosity doesn't demand answers, only wonder. Some nights when the world feels too loud, we look up, not for meaning really, just to remember how small our troubles are and how vast the dark can be. Tonight we're going somewhere far, past Mars, past the asteroid belt, to a place where one giant planet holds an entire universe in its orbit, Jupiter, and circling that giant 95 moons. 95 worlds each with its own story. Some are frozen, some are burning. Some hide oceans deeper than any on Earth. Before we drift into that darkness together, I want to say something softly. If these quiet journeys bring you peace, you might like to stay a while. You can gently tap the like button if this feels right to you. Subscribe if you'd like more stories told in whispers. And ring the little bell not for noise, but so the next quiet night can find you again. No pressure, just an invitation. Now let's drift. Tonight we're visiting Jupiter's moons. Not all 95. That would take lifetimes. But we'll walk among the strangest ones, the volcanic one, the ocean one, the ancient one. We'll let the facts wash over us like waves, and if you fall asleep halfway through, that's exactly as it should be. You don't need to remember everything. Just rest and let wonder do the listening. Jupiter sits almost 500 million miles from the Sun, 5 times farther than Earth. Out there, sunlight arrives weak and cold, barely a whisper of warmth. And yet, orbiting that giant, there's a moon covered in volcanoes. Another moon hides an ocean twice the size of all Earth's oceans combined. Another has a magnetic field stronger than some planets. How is that possible? How can dead frozen worlds pulse with such life? The answer scientists suggest lies in something invisible: gravity. Not the gravity that keeps your feet on the ground. The gravity that pulls, squeezes, kneads these moons like dough. Jupiter is so massive, its gravity doesn't just hold these moons in orbit. It stretches them, compresses them, heats them from the inside out. It's a kind of cosmic torture, beautiful and endless. When Galileo Galilei first pointed his handmade telescope at Jupiter in January 1610, he saw something no human had ever seen: 4 points of light moving, not stars, not background noise, moons, orbiting another world. It shattered the idea that everything revolved around Earth. Suddenly the universe was larger, stranger, more indifferent to us than anyone had imagined. Those 4 moons, Io, Europa, Ganymede, and Callisto, we now call the Galilean moons. And they're still the most fascinating objects in the solar system. But Galileo only saw 4. We've found 91 more since then. Tiny things, most of them. Captured asteroids, tumbling rocks, pieces of cosmic debris pulled into Jupiter's orbit like moths to a flame. Some are only a few miles wide. Some orbit backward against the spin of everything else, proof that they came from somewhere far away and got caught. The solar system, it turns out, is not as orderly as we once believed. It's messy, chaotic, full of stolen moons and second chances. Think about that for a moment. Jupiter doesn't just have moons, it has a collection. A gallery of worlds it's gathered over billions of years, some born with it, some taken by force. It's like a museum of planetary history, each moon preserving a different chapter. Some chapters are written in ice, some in sulfur and fire, some in ancient stone that hasn't changed in 4 billion years. Here's a question for you. If you could visit one moon, just one, which would it be? The one with volcanoes, the one with a hidden ocean, the one that's older than memory itself. Hold that thought gently. Don't answer out loud. Just let it sit there while we continue. Scientists didn't always care about moons. For most of history, moons were footnotes. Interesting maybe, but not important. Planets were the main event. Then we sent spacecraft, Voyager 1 and Voyager 2 in the late 1970s, Pioneer 10 and 11 before them. These machines flew past Jupiter and sent back images that changed everything. Suddenly, moons weren't boring. They were worlds, complex dynamic alive in ways we'd never imagined. The Voyager missions revealed that Io, the innermost of the Galilean moons, was erupting, not with quiet lava flows like Hawaii, with plumes of sulfur shooting 200 miles into space, higher than the International Space Station orbits Earth. Europa's surface, meanwhile, was covered in cracks like a frozen lake that had been walked on too soon. And beneath those cracks, scientists suggested might be water, liquid water, an entire ocean warmed by the same tidal forces that made Io explode. This wasn't science fiction. This was data. Hard, measurable, undeniable. And it rewrote the rules of where life could exist. For decades, we thought life needed three things: liquid water, energy, organic molecules. And we thought all three required sunlight. Plants make food from sunlight. Animals eat plants. Everything we believed traced back to a star. But then we found ecosystems on Earth that didn't need the sun. Deep-sea hydrothermal vents. Cracks in the ocean floor where superheated water pours out. And around those vents, entire communities thrive. Tube worms, shrimp, bacteria that eat chemicals, not light. Life, it turned out, was more creative than we gave it credit for. If life can exist in the darkness of Earth's oceans, why not Europa's? Why not in the warm water beneath Enceladus Saturn's icy moon? Suddenly, the search for life expanded. It wasn't just about finding another Earth. It was about finding another ocean, another warm crack in the ice, another place where chemistry could become biology. Jupiter's moons offered that hope, not because they're like Earth, because they're not. Because they prove that the universe has more than one way to make a world interesting. Some of Jupiter's moons are so small, they don't even have names yet, just numbers. S2003J2, S2011J1. Provisional designations waiting for someone to study them long enough to earn a proper name. Imagine that. A world floating in space and we haven't even decided what to call it. There's something humbling about that. Something that makes you realize how much we still don't know. But the big four, the Galilean moons, we know them well. Or at least we think we do. Every time we send a spacecraft, we learn something that contradicts what we thought before. Europa's ocean might be salty, or it might be acidic. Ganymede's magnetic field shifts in ways we didn't predict. Callisto's surface is older than we can measure a fossil from the solar system's birth. The more we look, the more questions we find. And maybe that's the point, not to have all the answers, just to keep looking. Jupiter itself is a mystery we're still unraveling. It's not a solid planet. It's mostly gas, hydrogen and helium swirling in bands of color. The Great Red Spot. A storm 3 times the size of Earth has been raging for at least 400 years, maybe longer. We don't know when it started. We don't know when it will end. It just spins endlessly, a hurricane that will outlive civilizations. And beneath that storm pressure, so much pressure that hydrogen stops being a gas and becomes a metal. A liquid metal ocean conducting electricity, generating a magnetic field, so powerful it traps radiation in belts around the planet. Those radiation belts would kill a human in minutes. They fry spacecraft electronics. They're one of the biggest challenges to exploring Jupiter's moons up close. But we try anyway. Because that's what humans do. We go where we're not welcome and try to understand it. The Juno spacecraft arrived at Jupiter in 2016. It's still there now, looping around the giant, in a long, stretched orbit, diving close to the cloud tops, and then swinging far out to avoid the worst of the radiation. Every orbit it gathers data, maps the magnetic field, measures the gravity, listens to the radio emissions that Jupiter makes, strange whistling sounds like a chorus of ghosts. And next, Europa Clipper, launching soon if it hasn't already by the time you hear this. A spacecraft designed specifically to study Europa, to fly past it dozens of times, scanning the ice with radar, sniffing for water, vapor plumes measuring the thickness of the shell, searching for the best place to land. Because one day, maybe in your lifetime, we'll send a robot down to Europa's surface. We'll drill through the ice and drop a submarine into that hidden ocean. and we'll see what's there. Will we find life? No one knows. The ocean might be empty, sterile, a chemical soup with no spark. Or it might be full of things we've never imagined: microbes, jellyfish made of ammonia, creatures adapted to eternal darkness and crushing pressure. The odds are small, but they're not zero. And even if we find nothing, the search itself is worth it, because it forces us to ask better questions. What is life? Does it need DNA? Does it need cells? Can it exist in forms we wouldn't recognize? Every world we explore teaches us something about the boundaries of possibility. Jupiter's moons are a laboratory, a place where we can test our assumptions, where we can see what happens when you take a world and squeeze it with gravity, or freeze it with distance, or bake it with radiation. Each moon is an experiment that's been running for billions of years. All we have to do is read the results. So tonight we'll walk through that laboratory together. Slowly, gently, we'll visit the volcanic moon, the ocean moon, the giant moon, the ancient moon. We'll talk about irregular moons and lost moons and moons that shouldn't exist. And if your eyes get heavy, let them close. If your thoughts drift away, let them go. This isn't a test, it's a story. And stories are meant to be felt, not memorized. The universe is vast, cold, indifferent. But it's also full of wonder, and sometimes in the quiet hours before sleep, that's enough. To know that somewhere far beyond the noise of Earth, there are volcanoes erupting on a moon no human has ever touched, oceans swirling beneath ice no one has ever seen, worlds waiting patiently for us to arrive. We're going to visit the first of those worlds now, a moon that never sleeps, a moon painted in sulfur and fire, a moon where the ground itself is alive, constantly reshaping, erupting, glowing in the dark. Its name is Io. And it's unlike anything else in the solar system. Io doesn't look like a moon. It looks like a pizza. That's what the scientists said when they first saw the images. A celestial pizza modeled with yellow, orange, red, white. Colors that shouldn't exist on a frozen rock 500 million miles from the sun. Colors that belong to sulfur, not ice, to fire, not frost. March 8, 1979. Voyager 1 was leaving Jupiter's system, its cameras pointed back for one last look. Linda Morabito, a navigation engineer at NASA's Jet Propulsion Laboratory, was processing the images. Routine work. She was looking for stars, checking the spacecraft's position. And then she saw something that didn't make sense. A plume rising from Io's surface. Not a crater, not a mountain. A cloud umbrella shaped, reaching 200 miles into space. At first she thought it was a moon, another satellite hiding behind Io. But it wasn't moving like a moon. It was moving like smoke, like an explosion frozen in time. She checked the data again, measured the angles, calculated the height, and then she realized what she was seeing: a volcano, erupting, active, right now. It was the first time humans had witnessed active volcanism beyond Earth, the first proof that other worlds weren't just dead rocks waiting in silence. They were alive, breathing, bleeding. Io wasn't sleeping. It was screaming. Scientists scrambled to reanalyze the earlier flybys. How had they missed this? Voyager had passed Io weeks before, and no one noticed. They went back through the images frame by frame, looking for clues. And there they were. Plumes, lava lakes, hot spots glowing in the infrared. Io wasn't just volcanic. It was the most volcanically active body in the entire solar system. More active than Earth, more active than Venus, more active than anything we'd ever imagined. 400 volcanoes. That's the current count, though. The number keeps changing. Some erupt constantly. Some pulse on and off like a heartbeat. Some shoot sulfur dioxide gas hundreds of miles high, where it freezes instantly and falls back down as snow. Sulfur snow. Yellow and toxic, covering the surface in drifts that never melt. Earth, by comparison, has around 1,500 volcanoes, but most of them are dormant, sleeping, Eos are awake, all of them, all the time. The surface is so young, so constantly renewed by lava, that there are almost no impact craters. Every scar gets erased, every crater gets filled. Eo's skin regenerates faster than we can map it. Why? What makes Io so violent? The answer is gravity, but not the way you might think. Most people assume Io is hot because it's close to Jupiter, closer to the giant, closer to the heat. But that's not how it works. Jupiter isn't a star. It doesn't produce heat the way the sun does. Jupiter is cold, a gas giant with no surface, just layers of cloud and pressure getting denser and denser until hydrogen becomes liquid metal. There's no furnace inside Jupiter, no core burning like Earth's. Io's heat comes from being pulled apart, stretched, compressed, kneaded like dough. Jupiter's gravity is immense, strong enough to hold Io in a tight orbit. But Io isn't alone. Europa and Ganymede orbit farther out, and their gravity tugs on Io too. Every time Io swings around Jupiter, it gets pulled one way. Every time Europa and Ganymede pass by, they pull another way. Back and forth, in and out. The moon flexes. Its shape changes, bulging and contracting with every orbit. That flexing generates heat, friction. Deep inside, Io rock grinds against rock. Minerals melt. Magma rises. And because Io is relatively small, that heat has nowhere to go but out. So it erupts. Again and again, a cosmic pressure cooker with no relief valve. This process is called tidal heating, and it's one of the most important discoveries in planetary science, because it means you don't need sunlight to keep a world warm. You don't need a star nearby, you just need gravity. Strong, relentless, crushing gravity. Think about what that means for the search for life. If tidal heating can keep Io molten, it can keep other moons warm too. Europa's ocean, Enceladus, Titan. Worlds far from the sun, far from any obvious heat source, could still have liquid water. Warm pockets, places where chemistry could become biology. Io taught us that. A moon no one expected to care about. A moon that looked boring from a distance, until we got close. Until we looked. Here's something most people don't realize. Io loses material. Every second, tons of it. The volcanoes don't just erupt lava, they spew sulfur dioxide gas, which escapes into space. Io's gravity is weak, only 1/6 of Earth's, not strong enough to hold on to a thick atmosphere. So, the gas drifts away, forming a giant donut-shaped cloud around Jupiter, a torus, made of ionized sulfur and oxygen glowing faintly in the ultraviolet. Jupiter's magnetic field sweeps through this torus, dragging the particles along, accelerating them to incredible speeds. Some of those particles slam into Europa and Ganymede, sandblasting their surfaces. Others spiral down into Jupiter's atmosphere, creating auroras. Glowing curtains of light at the poles 1,000 times brighter than Earth's northern lights. Io is feeding Jupiter, slowly, constantly, bleeding its atmosphere into space, and Jupiter drinks it up. In a way, Io is dying, losing mass, shrinking, but so slowly that it will take billions of years to notice. Does that make you feel anything? A moon that's destroying itself to fuel a planet's glow? There's something almost poetic about it, tragic, beautiful, like a star that burns too bright and knows it won't last. Scientists estimate Io loses about 1 ton of material every second. Over billions of years, that adds up. Some models suggest Io has lost several kilometers of surface material since it formed. The moon we see today is smaller than the moon that was born, a ghost of its former self. And yet it keeps erupting, keeps renewing, keeps fighting entropy. The lava on Io isn't like Earth's lava. It's hotter, much hotter. Some flows reach temperatures of 1,600 degrees Celsius. That's hotter than any lava on Earth today. In fact, it's similar to the lava that flowed on Earth billions of years ago, back when the planet was young and the mantle was still molten. Io, in a sense, is a window into Earth's past, a living museum of what our world used to be. But it's also alien. The composition is different. Earth's lava is mostly basalt-rich in silicates. Io's lava contains more sulfur, more exotic minerals. And the sulfur gives Io its colors: yellow sulfur, red sulfur, white sulfur dioxide frost, orange sulfur compounds. It's a painter's palette, but the paint is poison. If you stood on Io's surface, you'd be bombarded by radiation. Jupiter's magnetic field channeled high-energy particles into the space around Io, creating a radiation environment so intense it would kill you in hours. Your spacesuit would degrade, your electronics would fail, the ground beneath your feet would shift, crack, ooze. You'd hear nothing because there's no air to carry sound, but you'd see everything: plumes rising silently, lava glowing red and orange, the sky black and full of stars, with Jupiter hanging overhead, massive and striped, 60 times wider than the moon looks from Earth. It would be terrifying and beautiful and utterly inhospitable. No one will ever walk on Io, at least not for a very long time. The radiation makes it impossible. Even robots struggle. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, flew past Io several times. Each pass was a gamble. The radiation fried instruments, corrupted data, shortened the mission's life. But the images it sent back were worth it. High-resolution maps of the surface, thermal readings of the lava lakes, evidence of mountains taller than Everest made not of rock, but of sulfur and silicate compounds piled up by repeated eruptions. One of those mountains, Bossale Montes, rises nearly 18 kilometers high. That's more than twice the height of Everest. And it's not a volcano, it's just a mountain, built by tectonic forces we don't fully understand. Io's crust is constantly shifting, folding, collapsing under its own weight. The entire surface is unstable, a jigsaw puzzle that never stays solved. There's a lava lake on Io called Loki Patera, named after the Norse trickster god. It's the most powerful volcano in the solar system. Not the tallest, not the most dramatic, but the most energetic. It releases more heat than all of Earth's volcanoes combined. The lake is roughly 200 kilometers across, filled with molten rock that churns and overturns in cycles. Every few hundred days, the entire lake resurfaces. Old crust sinks, new lava rises. It's like watching the Earth's mantle in fast forward. Scientists study Loki Patera to understand how Earth's interior works, how magma moves, how heat escapes. Io is a laboratory, a place where the processes that shape planets are laid bare, happening fast enough to observe in real time. On Earth, these processes take millions of years. On Io, they take months. And yet, for all its violence, Io has a rhythm. The eruptions aren't random. They follow patterns. Some volcanoes erupt on schedule, almost like clockwork. Others respond to stress triggered by the gravitational pull of Europa and Ganymede as they align. It's a dance, chaotic but structured, wild but predictable. There's a lesson in that, maybe, that even in chaos there's order, that even a world being torn apart can find a balance. Io doesn't fight the gravity that tortures it. It adapts. It endures. It transforms pain into energy, destruction into creation. Every eruption is an ending and a beginning. If you've ever felt pulled in different directions, stretched too thin, crushed by forces you can't control, maybe there's something to learn from Io. Not that suffering is beautiful, but that resilience can be. That even when you're breaking, you're still here, still glowing, still erupting with something the universe has never seen before. Io will outlast us. Long after humanity is gone, Io will still be erupting, still painting itself in sulfur and fire, still feeding Jupiter's glow. It doesn't care that we named it, doesn't care that we study it. It just is. And maybe that's enough. But we're not staying on Io. There's another moon waiting, one that's quieter, colder, hiding something beneath a shell of ice that might be the most important discovery in the history of science. A moon that whispers instead of screams. A moon that keeps its secrets locked away deep below the surface, where no sunlight has ever touched. Europa looks smooth from a distance, clean, almost polished, like a cue ball made of ice reflecting sunlight in a way that makes it glow faintly blue-white against the darkness. But get closer and you see the cracks, thousands of them, crisscrossing the surface like veins. Like a frozen lake someone walked on too soon, like something underneath is trying to get out. Beneath that ice, scientists believe there's an ocean. Not a small one, not a puddle trapped in a crater. An ocean that contains twice as much water as all of Earth's oceans combined. Liquid, moving, possibly warm. And it's been there hidden for billions of years. If life exists anywhere else in our solar system, Europa is where we're most likely to find it. Galileo saw Europa in 1610, the same night he discovered Io, Ganymede, and Callisto, 4 moons moving around Jupiter like planets around the sun. He called them the Medicean stars, hoping to flatter his patron, the Medici family. The name didn't stick. But the discovery did. It was proof that not everything in the universe revolved around Earth. A small shift in perspective that changed everything. For centuries, Europa was just a point of light. One moon among many. No one suspected it was special. No one imagined what it was hiding. It wasn't until the Voyager missions in 1979 that we got our first real look. And even then, the images were puzzling. Europa's surface was young, too young, almost no craters. That meant something was erasing them. Resurfacing the moon. But how? The answer came slowly, piece by piece. Data from Voyager, data from Galileo, data from ground-based telescopes analyzing the light reflecting off Europa's surface. The ice wasn't static. It was floating, moving, cracking and reforming like sea ice on Earth. And beneath it, something was pushing, warping, flexing. Tidal heating. The same force that tortures Io. But on Europa, the effect is gentler. Europa is farther from Jupiter, so the gravitational pull isn't as extreme. It doesn't melt rock, it melts ice. And beneath that, melted ice water flows. The evidence is everywhere once you know what to look for. The cracks called lineae stretch for thousands of kilometers. Some are bright, filled with fresh ice that welled up from below and froze. Some are dark, stained with minerals and salts dragged up from the ocean. The pattern suggests the ice shell is thin in some places, maybe only 15 kilometers thick. On a moon 3,000 kilometers wide, that's barely a skin. Scientists have measured Europa's magnetic field, or rather the way it responds to Jupiter's magnetic field. Europa doesn't generate its own field like Earth does. But when Jupiter's field sweeps past, it induces a secondary field in Europa. That only happens if there's something conductive inside, something salty, salt water, an ocean rich in dissolved minerals sloshing beneath the ice with every orbit. There's more, spectroscopy. The analysis of light shows traces of sodium chloride on the surface, table salt, the kind you'd find in Earth's oceans. It's not everywhere, just in certain areas clustered around the youngest cracks, as if brine salty water seeped up through fractures and evaporated, leaving the salt behind. A chemical signature, a whisper from below. And then there are the plumes. In 2012, the Hubble Space Telescope detected something unexpected: water vapor, erupting from Europa's south pole, not constantly, intermittently, like geysers, like the moon was exhaling. Follow-up observations confirmed it. Europa is venting water into space. Not much, not enough to see with the naked eye, but enough to prove the ocean is real, enough to prove it's connected to the surface. Imagine what that means. You wouldn't have to drill through 15 kilometers of ice to reach the ocean. You could fly through a plume, collect samples, analyze them, look for organic molecules, for amino acids, for anything that suggests chemistry is doing more than just chemistry down there. The Europa Clipper mission is designed to do exactly that. Launching in 2024, it will spend years orbiting Jupiter, flying past Europa nearly 50 times. Each pass will bring it within 25 kilometers of the surface, close enough to taste the plumes, close enough to map the ice with ground-penetrating radar, close enough to measure the thickness of the shell and pinpoint the best places to land. But Europa Clipper won't land. It's a reconnaissance mission, a scout. Its job is to gather data so that future missions, landers, and submarines know where to go. Because landing on Europa won't be easy. The surface is bombarded by radiation. Charged particles from Jupiter's magnetosphere slam into the ice at relativistic speeds, breaking molecular bonds, creating hydrogen peroxide and sulfuric acid. The ice isn't pure. It's toxic, hostile, and yet beneath that ice, the ocean might be the most welcoming place in the solar system, shielded from radiation, warmed by tidal heating, rich in minerals leached from the rocky seafloor. It's not so different from Earth's deep oceans, and we know life thrives there. In 1977, scientists discovered hydrothermal vents on Earth's ocean floor, cracks in the crust where superheated water, rich in chemicals, pours into the freezing abyss. Around those vents, ecosystems flourish, tube worms as tall as a person, eyeless shrimp, bacteria that eat hydrogen sulfide, a compound toxic to most life. These organisms don't need sunlight. They don't need photosynthesis. They build their food from chemistry alone. Chemosynthesis, life powered by the heat of the Earth's core. If Earth's ocean floor can support life without sunlight, why not Europa's? The conditions are similar: liquid water, heat, chemicals. The ingredients are there. All that's missing is time, and Europa has had plenty of that. 4 billion years, longer than life has existed on Earth. Of course, there's no guarantee. Europa's ocean might be lifeless. The water might be too acidic, too salty, too cold despite the heating, or life might have started and gone extinct long ago, leaving nothing but fossils buried in the ice. We don't know. We can't know. Not yet. But the possibility is enough. The idea that somewhere right now beneath the ice of a moon, 500 million miles away, something might be swimming. Something that evolved independently of Earth. Something that would prove life isn't a fluke. That it's a natural consequence of chemistry and time. That's what makes Europa so important. It's not just about finding life. It's about understanding what life is, whether it's unique to Earth or common in the universe. Whether DNA is the only way or just one way. Whether consciousness, intelligence, culture could emerge in forms we've never imagined. Europa challenges our assumptions. On Earth, we think of the ocean as a place connected to the sky. Fish swim near the surface. Whales breathe air. Even deep sea creatures depend indirectly on the sun. Dead plankton sink. Nutrients cycle. The ocean and the atmosphere are linked. But Europa's ocean has no sky, no atmosphere, no sunlight reaching down. It's a closed system, sealed beneath ice. If life exists there, it's been isolated for billions of years, cut off from the surface, cut off from space, a separate biosphere, a second genesis. What would that life look like? Would it have eyes, even though there's no light? Would it have shells? Even though there's no need for protection from predators that might not exist? Would it be microbial, simple, invisible, or complex, organized, aware? Scientists debate this endlessly. Some think Europa's ocean is too young, too sterile. Others think it's teeming. We build models, run simulations, argue over the pH, the temperature, the nutrient availability. But in the end, we're guessing. We're extrapolating from one data point, Earth, a sample size of one. That's why we have to go. To see for ourselves, to stop guessing and start knowing. Here's something most people misunderstand. Europa isn't frozen because it's far from the sun. Distance matters, yes. But the real reason Europa has ice is because it has water. and water, when exposed to the vacuum of space, freezes. Even if Europa were closer to the sun, it would still have ice on the surface. The ocean exists because of internal heat, not external warmth. The ice exists because there's no atmosphere to hold in that heat. It's a delicate balance. Too much tidal heating, and the ice melts completely. The ocean would be exposed, and it would evaporate into space. Too little heating, and the ocean freezes solid. Europa sits right at the edge. Enough heat to stay liquid. Enough cold to stay covered. A Goldilocks zone, not based on distance from a star, but on gravitational torture. The ice itself is fascinating. Scientists believe it's layered. The top layer is hard, brittle, ancient, scarred by impacts and radiation. Beneath that, a softer layer, warmer, more pliable. And beneath that, the slush zone, a transition between solid and liquid where ice crystals float in water like icebergs in reverse. And finally, the ocean, pure liquid, dark, silent, waiting. Some researchers think the ocean might be shallow in places, only a few kilometers deep. Others think it could be 100 kilometers deep or more, deep enough to swallow Mount Everest and still have room to spare. We won't know until we send sonar down there, until we map the seafloor, and what's on that seafloor rock. Europa's core is rocky like Earth's mantle, and where water touches rock chemistry happens. Minerals dissolve, elements interact. Hydrothermal vents might exist just like on Earth. Warm plumes of mineral-rich water, rising from cracks in the seafloor, creating oases of heat in an otherwise frigid ocean. If Europa has vents, it has energy. And if it has energy, it might have life. There's a thought experiment scientists like to pose. If you could send a message to life on Europa, what would you say? Not that they could hear you, not that they'd understand. But if you could, what would you want them to know? That they're not alone, that we're searching for them, that we're kinborn of the same universe shaped by the same physics, dreaming the same question. Is there anyone else out there? Maybe silence is the better answer. Maybe the kindest thing we can do is leave them undisturbed. Let them evolve if they exist without interference, without contamination, without the burden of knowing about us. But curiosity is hard to resist, and Europa is calling. We've talked about 2 moons now, one that burns, one that hides. But there's a third moon larger than both, larger than some planets. A moon that shouldn't be a moon at all. A moon with its own magnetic field, its own atmosphere, its own strange contradictions. A moon that makes you question what we even mean when we say the word moon. There's a rule in astronomy that seems obvious. Planets are big, moons are small. Planets orbit stars, moons orbit planets. Simple, clean. Except Ganymede breaks that rule quietly without making a fuss. Ganymede is larger than Mercury, larger than Pluto. If it orbited the Sun instead of Jupiter, we'd call it a planet without hesitation. But it doesn't, so we call it a moon. And that label scientists suggest might be limiting the way we think about it. Ganymede is the largest moon in the solar system, 5,262 kilometers in diameter. That's about 8% bigger than Mercury and almost 3/4 the size of Mars. It has more volume than all the other Jovian moons combined. If you stood on Ganymede and looked up, Jupiter would fill half the sky. A giant striped marble bright enough to cast shadows even in the dead of night. But size isn't what makes Ganymede strange. What makes it strange is what's inside. Ganymede is the only moon in the solar system with its own magnetic field, not induced like Europa's, not borrowed from its parent planet, its own. Generated deep inside from a liquid iron core spinning and convecting, creating currents of electricity that wrap the moon in an invisible shield, a magnetosphere. Tiny compared to Earth's, fragile compared to Jupiter's, but real, persistent. Proof that Ganymede is more than a frozen ball of ice and rock. It's a world, complex, layered, differentiated. And it's been hiding that complexity for a very long time. When Galileo discovered Ganymede in January 1610, he had no way of knowing what he was looking at. His telescope was crude, barely strong enough to resolve Jupiter's moons as points of light. He watched them move night after night, sketching their positions, trying to understand the pattern. And slowly, the truth emerged. They were orbiting Jupiter, not the Earth, not the Sun. Jupiter. It was a small observation, but it shattered centuries of assumption. If moons could orbit Jupiter, then Earth wasn't the center of everything. The universe was larger, stranger, less concerned with us than we wanted to believe. Ganymede at the time was just one of four, bright, steady, unremarkable. It would be another 369 years before we got close enough to see its face. Voyager 1 flew past Ganymede in March 1979. The images it sent back were puzzling. The surface was a patchwork. Dark regions, ancient and cratered next to bright regions, young and grooved. It looked like two different moons stitched together. Scientists didn't know what to make of it. Some thought the dark areas were older ice stained by dust and radiation. Others thought the bright areas were fresh ice exposed by impacts or volcanic activity. Both were partly right. The Galileo spacecraft, which arrived in 1995 and orbited Jupiter for 8 years, gave us a clearer picture. Ganymede's surface is divided into two terrains. Dark terrain, which covers about a third of the moon, is old, 4 billion years old, saturated with craters. A fossil record of the solar system's violent youth when asteroids and comets swarmed like locusts, smashing into anything in their path. The bright terrain is younger, maybe 2 billion years old, maybe less. It's covered in grooves, long parallel ridges that stretch for hundreds of kilometers. Scientists believe these grooves formed when the ice crust stretched and cracked, pulled apart by tidal forces or internal shifts. Fresh ice welled up from below, filling the gaps, freezing smooth, over and over, resurfacing the moon in sections. Why didn't the whole surface get resurfaced? Why did some areas stay ancient while others renewed? No one knows for sure. It might be related to Ganymede's orbit, the way it interacts with Europa and Io, the way Jupiter's gravity pulls unevenly. Or it might be something internal, a quirk of how heat flows through the moon's interior, concentrating in some regions and avoiding others. Ganymede, like Europa, is thought to have a subsurface ocean, not as close to the surface, not as accessible, but there, buried deep beneath 100 kilometers of ice. Scientists inferred its existence from the magnetic field measurements. The way Ganymede's field wobbles as it orbits through Jupiter's field suggests there's a conductive layer inside. Salt water. An ocean sandwiched between layers of ice, some of which might be under so much pressure they turn into exotic forms of ice that don't exist naturally on Earth. Ice 6, Ice 7. Phases of water that are solid even at high temperatures because the pressure is so intense. Imagine that. Water so compressed it behaves like rock. And beneath that liquid water, dark, cold, cut off from the surface by a barrier thicker than Earth's crust. If there's life in Ganymede's ocean, it's more isolated than Europa's. Harder to reach, harder to detect, but not impossible. And the fact that it exists at all is remarkable. A moon orbiting a planet, orbiting a star with an ocean buried so deep that sunlight has never touched it and never will. And yet, it endures, liquid, moving. Kept warm by the memory of Ganymede's formation, by the slow decay of radioactive elements in the core, by the faint tug of tidal forces that even this far out still matter. Ganymede's atmosphere is almost non-existent, thinner than a whisper, but it's there. Oxygen, not breathable, not concentrated. Just a few molecules per cubic centimeter liberated from the ice by radiation. Charged particles from Jupiter slam into the surface, break apart water molecules, and the hydrogen escapes into space while the oxygen lingers too heavy to drift away quickly. It's not enough to see, not enough to feel, but spectrometers can detect it, a chemical signature, a reminder that even in the vacuum of space chemistry never stops. Here's something that surprises people. Ganymede has auroras, not like Earth's northern lights, no colors, no shimmering curtains. Just faint glows in the ultraviolet invisible to the human eye, detectable only by instruments. They occur near the poles where Ganymede's magnetic field funnels charge particles down into the thin atmosphere. The particles collide with oxygen molecules, exciting them, making them glow for a fraction of a second before they relax back into darkness. It's beautiful in an abstract way. A moon with its own auroras, its own magnetic poles, its own weather if you can call the movement of a few stray atoms weather. Ganymede is a planet in everything but name. And maybe that's the real lesson, that the labels we use planet, moon, asteroid are human inventions. Convenient but arbitrary. The universe doesn't care what we call things. It just keeps creating them. Ganymede's core is thought to be iron, possibly mixed with sulfur, hot, molten, convecting in slow viscous currents that generate the magnetic field. The existence of that core tells us something important. Ganymede didn't just accumulate randomly from ice and rock. It differentiated. It melted at least partially early in its history. Heavy elements sank, light elements rose. The moon sorted itself into layers like a miniature Earth. That process requires heat, a lot of it. And the heat had to come from somewhere. Some came from radioactive decay. Uranium, thorium, potassium elements embedded in the rock, breaking down over billions of years, releasing energy. Some came from impacts. The early solar system was chaotic. Collisions were common. Every impact added kinetic energy, which turned into heat. And some scientists believe came from tidal heating, back when Ganymede's orbit was more eccentric, when the gravitational torture was stronger. Over time, the orbit circularized. The tidal heating weakened. The moon cooled. But the core, insulated by layers of rock and ice, stayed warm. And it's still warm now, still molten, still generating a magnetic field that shouldn't exist. There's a poetic irony in that. Ganymede is the largest moon, but it's also the quietest. It doesn't erupt like Io. It doesn't crack like Europa. It just sits there massive and cold, keeping its secrets locked beneath kilometers of ice. You could spend a lifetime studying Ganymede and still not understand it completely, because it doesn't reveal itself easily. It rewards patience, careful observation, the slow accumulation of data. Scientists study Ganymede to understand planetary formation, how worlds go from clouds of dust to differentiated bodies with cores, mantles, and crusts. Ganymede is a laboratory for that process, a place where we can see the results without the complications of a thick atmosphere or active geology obscuring the evidence. And there's another reason to study Ganymede. It might be a preview of the future. Earth's moon is slowly drifting away. Every year it recedes by about 3.8 centimeters. In billions of years, it will be too far away to cause significant tides. It will become a distant companion, cold and inert like Ganymede. Understanding Ganymede helps us understand what our own moon might become, what all moons become when the fire inside goes out and only the ice remains. But Ganymede isn't dead. Not yet. It still has a magnetic field, still has an ocean, still has grooves forming cracks, spreading a surface that remembers motion, even if that motion has slowed to a crawl. If you could visit Ganymede, you'd notice the gravity first. 1.4 meters per second squared. About 14% of Earth's. You could jump high, walk with a strange bounding gait, but you'd also feel the weight of Jupiter's presence. The planet's magnetosphere reaches out this far, wrapping Ganymede in a cocoon of charged particles. Radiation levels are lower than at Io or Europa, but still dangerous. You'd need shielding, a thick suit, a habitat buried beneath the ice. And what would you see? A landscape of contrasts, dark plains cratered and ancient stretching to the horizon. Bright grooves cutting across the plains like scars. The ice would be dirty, grayish. Not the clean white of fresh snow, but the tired white of ice that's been exposed to space for eons. and above Jupiter. Always Jupiter. Hanging in the sky 60 times wider than the full moon looks from Earth, striped, swirling. A reminder that you're not on a world of your own. You're on a moon, a satellite, a child orbiting a giant. Would that feel claustrophobic or liberating, to know that your world is defined by another, that your orbit, your day, your tides are all dictated by something larger? Maybe there's peace in that, in knowing your place, in accepting that you're part of a system, not the center of it. Ganymede teaches humility. It's bigger than some planets, but it's still a moon. It has a magnetic field, but it's still dwarfed by Jupiter's. It has an ocean, but it's buried too deep to touch. It's a world of almosts. Almost a planet. Almost independent. Almost understood. And maybe that's enough. Maybe the beauty isn't in being the biggest or the brightest or the most dramatic. Maybe it's in being complicated, layered, quietly fascinating. A puzzle that doesn't demand to be solved, but invites you to try anyway. There's one more moon in the Galilean quartet. One that doesn't hide oceans or erupt in fire. One that doesn't generate magnetic fields or crack under stress. One that just sits there untouched, unchanged, a witness to everything that's happened since the solar system began. A moon that remembers when the universe was young and violent and full of possibility. A moon that's forgotten nothing. Callisto is the moon that time forgot. Not because it's unimportant, because it's unchanged. For 4 billion years, while Io erupted and Europa cracked and Ganymede sorted itself into layers, Callisto just sat there, quiet, still, accumulating scars like an old soldier who's seen too many battles and stopped counting. Its surface is the oldest in the solar system. Every crater is a fossil, every impact a time stamp. If you want to know what the early solar system looked like when asteroids swarmed like angry bees and collisions were daily events, you look at Callisto. Because Callisto remembers. It's the archive, the record keeper, the moon that refused to forget. Callisto orbits farther from Jupiter than the other Galilean moons. Far enough that the tidal forces are weak, far enough that it never melted completely, never differentiated, never sorted itself into a core mantle and crust the way Ganymede did. It's just ice and rock mixed together, frozen in the configuration it had when it formed. A relic, a time capsule, a snapshot of what moons looked like before they grew up. Scientists call Callisto a dead moon. But that's not quite fair. It's not dead. It's patient, it's waiting, and in its stillness, it has something to teach us. When Voyager 1 photographed Callisto in 1979, the images were almost disappointing. No volcanoes, no grooves, no bright patches, just craters, thousands of them, overlapping layered piled on top of each other like memories that refused to fade. The surface was so saturated with impacts that there was barely any room left for new ones. Scientists measured the crater density and realized something astonishing. Callisto's surface was at equilibrium. Every new crater that formed erased an old one. The moon had reached a kind of cosmic balance where creation and destruction happened at the same rate. That balance took billions of years to achieve. And it tells us something profound, that even violence given enough time can reach a steady state. That chaos over eons becomes predictable. The largest feature on Callisto is Valhalla, not a crater in the traditional sense. A multi-ring basin, a scar so massive it's visible from millions of kilometers away. Valhalla is 3,800 kilometers across. That's about the width of the continental United States. At the center, a bright patch, the impact site, radiating outward concentric rings, ripples frozen in ice. Scientists believe Valhalla formed early in Callisto's history, when an asteroid the size of a mountain slammed into the moon at tens of kilometers per second. The impact released energy equivalent to millions of nuclear bombs. The ice shattered. Waves of shock propagated outward, flexing the crust, creating the rings. And then over time, the ice settled, relaxed. The rings became permanent. a reminder that even ice has memory. Valhalla isn't unique. Callisto has other multi-ring basins, Asgard, Adlinda, each one a monument to a moment of catastrophic violence, each one a chapter in the moon's long quiet story. Here's what most people get wrong about Callisto. They assume it's boring because it's not active, but inactivity is information. The fact that Callisto didn't melt, didn't crack, didn't resurface tells us something important about the conditions required for geological activity. It tells us that distance matters, that tidal heating has limits, that not every moon gets tortured by gravity. Callisto escaped that fate. It's far enough from Jupiter that the tidal forces are negligible. Its orbit is nearly circular, stable, predictable. There's no flexing, no grinding, no internal heat being generated. Callisto is cold inside, frozen, geologically dead, yes, but preserved, like a fossil frozen in amber. And that preservation makes it valuable, because Callisto's surface is a record of the solar system's history. Every crater is dated. Every impact tells a story. By studying the size and distribution of the craters, scientists can reconstruct the bombardment history of the entire Jovian system. They can figure out when the asteroids were most active, when the comets swept through, when things settled down. Callisto is a witness, and witnesses matter. There's evidence tentative and contested that Callisto might have a subsurface ocean, not like Europa's, not as accessible, but there, deep beneath the ice, insulated by kilometers of frozen crust, warmed by the slow decay of radioactive elements. The evidence comes from magnetic field measurements, just like with Europa and Ganymede. Callisto's field responds to Jupiter's in a way that suggests there's a conductive layer inside, salt water possibly, or a slush of ice and brine. If Callisto has an ocean, it's the most isolated one in the solar system, cut off from the surface by ice so thick and cold that nothing could tunnel through. No plumes, no cracks, no communication between the ocean and the vacuum above. If life exists there, it's completely alone. No sunlight, no external energy, just chemistry time and darkness. Would that kind of isolation be liberating or suffocating, to be so far removed from the rest of the universe that you don't even know it exists? To swim in an ocean with no surface surrounded by ice on all sides, living in a bubble that's been sealed for billions of years? There's something both terrifying and beautiful about that. A biosphere unto itself. Independent, self-contained, forgotten. Callisto's atmosphere is barely there. Thinner than Ganymede's, just a trace of carbon dioxide liberated from the ice by impacts and radiation. Not enough to breathe, not enough to see, but enough to detect. A chemical whisper, a sign that even the quietest worlds are never completely silent. The moon's surface is dark, darker than the other Galilean moons. Stained by eons of radiation and dust accumulation. The ice isn't pure. It's mixed with rock, with carbon, with organic molecules delivered by comets. Spectroscopy shows hints of tholins, complex organic compounds that form when simple molecules are exposed to radiation. Tholins are the building blocks of life. Not life itself, but the chemistry that could, under the right conditions, become life. Callisto has those building blocks, frozen, scattered across its surface like seeds waiting for spring. But spring never comes to Callisto. The temperature hovers around minus 160 degrees Celsius, cold enough to freeze carbon dioxide, cold enough to make methane solid. Nothing grows here, nothing changes. The tholins just sit there inert, a promise unfulfilled. And yet scientists are interested. Because Callisto is stable, predictable, safe. The radiation levels are lower than at the other Galilean moons. The surface is solid, not constantly resurfacing like Europa's or erupting like Io's. If humanity ever builds a base in the Jovian system, Callisto is the most likely candidate, a place to land, a place to stay, a place where the ground doesn't shift beneath your feet and the sky doesn't kill you instantly. Imagine that. A human outpost on Callisto, a dome of metal and glass perched on ice 4 billion years old. Inside, warmth, light, the hum of machinery. Outside, silence, craters stretching to the horizon. Jupiter hanging in the sky smaller than it looks from Io or Europa, but still massive, still beautiful. From Callisto, you'd have a front row seat to the Jovian system. You could watch Io erupt, track Europa's plumes, monitor Ganymede's magnetic field, and you'd be safe. Far enough from Jupiter that the radiation wouldn't kill you. Far enough from the other moons that their chaos wouldn't touch you. Callisto is the observer, the one who watches but doesn't participate. And maybe that's a role worth valuing. There's a philosophical question buried in Callisto's existence. Is change always better than stability? We celebrate Io for its volcanoes, Europa for its hidden ocean, Ganymede for its magnetic field. But Callisto is dismissed as boring, as dead, as a moon that failed to evolve. But what if stability is a kind of success? What if preserving the past is as important as creating the future? Callisto didn't erase its history. It kept it. Every crater, every impact, every scar. That takes a different kind of strength. Not the strength to change, but the strength to endure. Scientists study Callisto to understand what happens when a world doesn't evolve, when it stays frozen in its original state. And what they've found is surprising. Callisto isn't simple. It's complicated in different ways. Its surface is a palimpsest layers of history written over each other. Its interior might still have liquid water despite the cold. Its chemistry is rich, diverse, full of potential that's never been realized. Callisto is the moon that could have been, the moon that chose stillness over motion, the moon that said, "This is enough." And maybe there's wisdom in that, in knowing when to stop, when to rest, when to let the universe move around you without feeling the need to move with it. If you stood on Callisto and looked up, you'd see stars. More stars than you've ever seen from Earth, because there's no atmosphere to scatter the light, no air pollution, no city glow, just stars, millions of them, sharp, clear, eternal, and among those stars, Jupiter. Smaller than it looks from the inner moons, but still dominant, still the center of everything. You'd also see the other moons, Io glowing faintly in the infrared, Europa a pinprick of light, Ganymede bright and steady, your siblings, your companions, all orbiting the same giant, all following the same rules, but each one different, each one unique. And you'd realize something, that being part of a family doesn't mean being the same. Callisto is different from Io, different from Europa, different from Ganymede, and that's okay. Difference is what makes the system work. If every moon were volcanic, the system would be unstable. If every moon cracked, there'd be no solid ground. Callisto's stillness balances Io's violence. Callisto's age balances Europa's youth. The system needs all of them, the loud ones and the quiet ones, the changing and the unchanging, the moons that scream and the moons that whisper. Callisto whispers. And if you listen closely, you can hear it. A story 4 billion years old. A story about endurance, about memory, about the beauty of being exactly what you are, even if the universe expects you to be something else. But Callisto is only one kind of moon, the kind that was born with Jupiter, the kind that grew up alongside the giant. There are other moons, smaller, stranger, moons that came from somewhere else, moons that were captured, stolen, pulled into orbits they never chose. Moons that tumble backward through space, defying the rules, refusing to conform. And those moons have stories too. Stories of wandering, of being lost, of finding a new home in the arms of a giant that wasn't theirs to begin with. Not all of Jupiter's moons were born there. Some were stolen, plucked from the asteroid belt or the outer reaches of the solar system, pulled into orbit by gravity so strong it wouldn't let them go. Those are the irregular moons, small, dark, tumbling through space in orbits that make no sense. Some circle Jupiter backward against the spin of everything else. Some are tilted at wild angles. Some are so far out they take more than 2 Earth years to complete a single orbit. They're outcasts, strangers, refugees from somewhere else, and they outnumber the regular moons 4-1. Jupiter has 95 known moons. Only the 4 Galilean moons and a handful of smaller inner moons were born in the disk of gas and dust that surrounded Jupiter during its formation. The rest, 79 of them, were captured, kidnapped, trapped in orbits they never chose, and each one tells a different story about where it came from and how it got here. The discovery of these irregular moons happens slowly, painstakingly, because they're small. Most are less than 10 kilometers across. Some are only a few kilometers. From Earth, even through the most powerful telescopes, they're just faint dots, barely distinguishable from background stars. It takes patience to find them, hours of observation, careful tracking, comparing images taken weeks or months apart to see what moved. In 1904, Charles Dillon Perrine discovered the first irregular moon using the Lick Observatory in California. He called it Himalaya, the 6th moon of Jupiter. It was a breakthrough, proof that Jupiter's family was larger than anyone had imagined. Over the next few decades, astronomers found a few more: Ilara, Pasiphae, Sinope. Each discovery required months of work. Each moon was a prize. But the real flood came later. In the late 1990s and early 2000s, when digital cameras replaced photographic plates and computers could process images faster than human eyes, Scott Shepard and his team at the Carnegie Institution for Science led the charge. They used the Subaru telescope in Hawaii and the Magellan telescopes in Chile, scanning the space around Jupiter night after night. And they found moons, dozens of them, tiny worlds no one knew existed. In 2003 alone, Shepard's team discovered 23 new moons. In 2018, they found 12 more. The count keeps rising, and with each new discovery, the picture gets more complicated. Because these moons don't fit neatly into categories, they cluster into groups, yes, but within those groups there's chaos, variation, individuality. Scientists have identified 4 main groups of irregular moons based on their orbital characteristics: the Himalaya group, the Ananke group, the Karm group, the Pasiphae group. Each group is named after its largest member, and each group researchers suggest might be the fragments of a single larger object that broke apart long ago. The Himalaya group orbits at a moderate distance from Jupiter, about 11 million kilometers out. Their orbits are prograde, meaning they circle in the same direction as Jupiter spins. That's unusual for irregular moons. Most captured objects end up in retrograde orbits because of the way gravity and momentum interact during capture. The fact that the Himalaya group is prograde suggests they might have been captured differently, or they might have formed closer to Jupiter and drifted outward over time. No one knows for sure. Himalaya itself is the largest of the irregular moons, about 170 kilometers across, big enough to be roughly spherical, pulled into a round shape by its own gravity. Its surface is dark, very dark, reflecting only about 4% of the sunlight that hits it. That's darker than asphalt, darker than coal. The darkness suggests the surface is covered in carbon-rich material, organic compounds, the same stuff that makes up asteroids in the outer belt. The Ananke group orbits farther out, about 21 million kilometers from Jupiter, and they're retrograde, circling backward against the flow. Their orbits are tilted inclined at steep angles relative to Jupiter's equator. Some tilt as much as 165 degrees, almost completely upside down. That's a signature of capture. When an object gets pulled into orbit by a passing planet, it doesn't line up neatly. It keeps whatever trajectory it had when it got caught. And if that trajectory was retrograde, it stays retrograde. Scientists believe the Ananke group might be the remnants of a larger moon that shattered, maybe from a collision, maybe from tidal stress as it was being captured. The fragments stayed close together, orbiting in a cluster like a flock of birds that refuses to separate. There are more than 20 moons in the Ananke group, and they all have similar colors, similar compositions, similar orbits. They're family, pieces of the same parent body. The Karm group is even farther out, 23 million kilometers, also retrograde, also tilted, and also scientists think the debris from a catastrophic breakup. The largest member, Karmi, is about 46 kilometers across. The smallest are only a few kilometers. Some are irregularly shaped, lumpy, tumbling end over end as they orbit. They don't have enough gravity to pull themselves into spheres. They're just chunks, rubble, cosmic shrapnel. And then there's the Pasiphae group, the outermost irregular moons. Some orbit as far as 24 million kilometers from Jupiter. At that distance, the sun's gravity is almost as strong as Jupiter's. These moons are barely held. A slight nudge, a close encounter with another moon, or a passing asteroid could knock them loose, send them drifting into space, free again. The Pasiphae group is retrograde, highly inclined, and scattered. The members don't orbit close together like the Ananke or Karm groups. They're spread out, lonely. Some scientists think they're not fragments of a single object, but separate captures. Different asteroids caught at different times that happen to end up in similar orbits by chance. Here's something that surprises people. These irregular moons are not stable, not in the long term. Their orbits are chaotic, influenced by the sun, by the other moons, by Jupiter's oblateness, the way the planet bulges at the equator. Over millions of years, their orbits shift, precess. Some will eventually collide with each other. Some will get ejected from the system entirely. Some might spiral inward and crash into Jupiter. The irregular moons are temporary, transient. They won't be here forever. In 1 billion years, Jupiter's family will look different. Some moons will be gone. New ones might be captured. The system is dynamic, always changing, always in flux, and that's humbling. To realize that even something as massive and permanent seeming as a moon can be temporary. That orbits are not forever. That everything given enough time drifts away or falls apart. One of the strangest irregular moons is Valetudo, discovered in 2018. It's tiny, only about 1 kilometer across. But what makes it strange is its orbit. Valetudo orbits prograde like the Himalaya group, but it's mixed in with retrograde moons. It's like a car driving the wrong way on a highway. Sooner or later, something's going to hit it. Scientists estimate that Valetudo will collide with another moon within the next 1 billion years. Maybe sooner. When that happens, both moons will shatter, the debris will scatter, and Jupiter will have a brief ring, a faint halo of dust and fragments glowing softly in reflected sunlight before it disperses into space or falls into Jupiter's atmosphere. Collisions between moons are not hypothetical. They've happened before. The groups themselves, the Ananke group and the Karm group, are evidence of past collisions, and they'll happen again. Because the irregular moons are crowded, their orbits intersect, and space, despite being vast, is surprisingly full of things that can run into each other. Think about what that means. Right now, as we speak, there are moons orbiting Jupiter that are on a collision course, moving slowly, inexorably, toward a moment of destruction that might not come for 1 million years, but is coming nonetheless. And there's nothing anyone can do about it. It's already written, already inevitable. Does that make you feel anything? The certainty of it, the patience of cosmic catastrophe. Time moves differently out there. What seems stable on human timescales is chaos on astronomical ones. Most of the irregular moons don't have proper names yet, just designations. S2003J2, S2016J1. Temporary labels waiting for someone to study them long enough to earn a permanent name. The International Astronomical Union has rules for naming Jupiter's moons. They have to be named after figures from Greek and Roman mythology associated with Jupiter or Zeus, lovers, descendants, companions. The list is long, but not infinite. And as we keep finding moons, we're running out of names. Some scientists have suggested we stop naming them. Just number them. Treat them like asteroids. Because functionally that's what they are, asteroids that got caught. But there's resistance to that idea. Because names matter. Names make things real. A moon called S2003J2 is abstract. A moon called Valetudo is a world. Even if it's just a kilometer-wide rock tumbling through the void, the irregular moons are hard to study. Too small, too faint, too far away. We don't have high-resolution images of most of them, just dots, specks of light. We can measure their orbits, estimate their sizes, analyze the light they reflect to guess at their composition. But we don't know what their surfaces look like. We don't know if they have craters, or if they're smooth, or if they're shaped like potatoes or eggs or something we've never seen before. That uncertainty is frustrating, but it's also thrilling, because it means there are still mysteries, still unknowns, still places in our own solar system where no human eye has ever looked closely. And that's rare. Most of the solar system has been mapped, photographed, analyzed, but the irregular moons of Jupiter are still wild, still unexplored, still waiting. If you could visit one of these moons, which would you choose? The largest Himalaya, with its dark surface and prograde orbit, or one of the tiny retrograde ones tumbling backward through space so far from Jupiter that the giant looks small in the sky, or maybe Valetudo, the moon on borrowed time, circling the wrong way, waiting for the collision that will end it. Each choice tells a different story. Each moon offers a different perspective, but all of them share one thing. They're survivors. They were torn from their original homes, flung into new orbits, and they're still here, still circling, still holding on. There's a lesson in that, about resilience, about adapting to circumstances you didn't choose, about finding a new home in a place that wasn't meant for you. The irregular moons didn't ask to be captured, but they're making the best of it, orbiting quietly, existing, enduring. And maybe that's enough. To exist, to endure, to keep moving even when the path makes no sense and the destination is uncertain. The irregular moons don't know why they're here. They just are, and they'll keep being here until they're not. But there's more to this story, because some of Jupiter's moons are even stranger than the ones we've found. Some have been lost, observed once and never seen again. Ghosts in the data, mysteries that refuse to be solved. And then there are the moons we haven't found yet. The ones hiding in the glare, the ones too small or too far to detect. The ones waiting patiently for us to build better telescopes and look a little harder. There's a moon orbiting Jupiter that we've lost. Not physically. It's still there somewhere tumbling through space in an orbit we calculated years ago. But we can't find it. We've looked, pointed telescopes at the coordinates where it should be, scanned the surrounding space. Nothing. The moon vanished, or rather, we lost track of it. And now, it's a ghost, a designation in a database. S2003J2, a world we saw once and never saw again. How do you lose a moon? It seems impossible. Space is big, yes, but moons don't just disappear. They follow predictable paths, orbits governed by gravity mathematics laws that don't change. If you know where a moon is and how fast it's moving, you should be able to predict where it'll be years, decades, even centuries later. But prediction requires precision, and when the object is small, faint, and far away, precision is hard. S2003J2 was discovered in 2003 by Scott Shepard's team. They saw it in a series of images taken with the Magellan telescope in Chile, a faint dot moving against the background stars. They tracked it for a few nights, calculated a rough orbit, gave it a provisional designation, and then they moved on to other targets. Because there are always more targets, more moons to find, more data to process. The plan was to come back later, refine the orbit, get better measurements. But when they tried, the moon wasn't there. It should have been. The math said it should be in a specific patch of sky at a specific time, but the patch was empty. They searched nearby areas. Nothing. They checked the calculations, rechecked. The numbers were right. The moon was just gone. What happened? Most likely the initial orbit calculation was slightly off. Even a small error, a fraction of a degree, compounds over time. After a year, that error might place the moon hundreds of thousands of kilometers from where you expect. And when you're searching for something only a few kilometers wide, hundreds of thousands of kilometers is an impossible gap. The moon is still out there. We just don't know where. S2003J2 isn't the only lost moon. There are others. S2000J11 was observed a few times in 2000 and then lost. It was recovered in 2010, a full decade later, after astronomers refined their search techniques and got lucky. But S2003J2 remains missing. A reminder that even in the age of computers and digital imaging, the universe is still good at hiding things. Losing a moon sounds like failure, and in a sense it is. But it's also instructive. It teaches us about the limits of observation, about how hard it is to track small objects at vast distances, about the importance of follow-up. You can't just discover something and assume you'll always be able to find it again. You have to keep watching, keep refining, keep caring. And there's something poetic about lost moons, about the idea that some things once seen slip back into obscurity, that the universe doesn't owe us clarity or convenience. That knowledge once gained can be lost again if we're not careful. But lost moons are only part of the story, because for every moon we've lost, there are probably dozens we haven't found yet. Scott Shepard estimates that Jupiter might have more than 600 moons. 600. Most of them tiny, less than a kilometer across, too small to see with current telescopes, too faint to distinguish from background stars, hiding in plain sight. The ones we've found, the 95 confirmed moons, are just the largest and brightest, the easiest to detect. As our technology improves, as our telescopes get bigger, and our cameras get more sensitive, we'll find more, and more, until the list becomes so long that naming them individually becomes impractical. Some scientists think the number might be even higher. If you count every rock, every boulder larger than a meter or two, the number could be in the thousands, or tens of thousands. At that point, the distinction between a moon and a piece of debris becomes blurry. Where do you draw the line? What's the minimum size for something to count as a moon? The International Astronomical Union doesn't have a strict definition. Generally, if an object is in orbit around a planet and large enough to be detected and tracked, it gets classified as a moon. But that's a practical definition, not a physical one. There's no magic size threshold, no clear boundary. Just a gradient from definitely a moon to probably just a rock. And that ambiguity is fascinating, because it forces us to ask deeper questions. What is a moon, really? Is it about size, about shape, about origin? Or is it just about being noticed, about having someone care enough to look? One of the strangest recent discoveries is a moon that orbits the wrong way in the wrong place. Valetudo, which we mentioned earlier. But there's another one. S2016J3, also known as Ursa. It's small, less than 3 kilometers across, and it orbits in a region between the regular and irregular moons, a no man's land, a place where most objects don't survive because the gravitational interactions are too chaotic. Ursa's orbit is inclined, tilted, not as extreme as the retrograde moons, but not aligned with Jupiter's equator either. It crosses paths with other moons, comes close. Too close for comfort. Scientists calculate that Ursa is in an unstable orbit. It might survive for a few million years, maybe 10 million, but eventually it will collide with something or get ejected. It's living on borrowed time. Why is Ursa there? How did it end up in such a strange orbit no one knows? It might be a fragment from a larger moon that broke apart, or it might be a captured asteroid that got caught in a weird resonance with Jupiter's gravity, or it might be something else entirely, a scenario we haven't thought of yet. That's the thing about moons. Every time we think we understand the patterns, we find an exception, an outlier, a moon that doesn't fit. And those exceptions are where the real science happens, because they force us to revise our models, to think harder, to admit that we don't know as much as we thought. The tools we use to find moons have changed dramatically over the past century. When Galileo discovered the first 4 moons in 1610, he used a telescope with a magnification of about 20 times, barely enough to resolve Jupiter as a disk. When Perrin discovered Himalaya in 1904, he used photographic plates, glass coated with light-sensitive chemicals, exposures that took hours, images that had to be developed in a dark room and examined by hand. Now we use digital cameras, CCDs and CMOS sensors that can detect individual photons. We can take thousands of images in a single night and process them with algorithms that automatically identify moving objects. We can search areas of sky in minutes that would have taken decades with photographic plates. And yet, even with all that technology, finding moons is hard because they're faint, so faint that they're barely brighter than the noise in the detector. You have to stack multiple images, compare them, look for patterns. It's like trying to spot a firefly in a thunderstorm. Possible, but not easy. Scott Shepard's team has a technique they call shift and stack. They take dozens of images of the same region of sky over several hours or nights. Then they shift each image slightly to account for the predicted motion of a moon. If there's a moon there, it will appear as a bright point in the stacked image. If there's nothing, the stack will be empty. It's elegant, efficient, and it works. But it only works if you know roughly where to look. If the moon is somewhere unexpected, you'll miss it. And if the moon is too faint, even stacking won't help. There's a limit to what we can see, a horizon beyond which objects simply disappear into the darkness. That horizon is shrinking. New telescopes are being built. The Vera Rubin Observatory, the extremely large telescope, instruments with mirrors 10 meters across, 30 meters across, cameras with billions of pixels, sensitivity that will make current technology look primitive. When those telescopes come online, we'll find more moons, many more. Jupiter's family will grow, and it's not just Jupiter. Saturn has 83 confirmed moons. Uranus has 27. Neptune has 14. Every time we look closer, the numbers increase. The solar system is crowded, full of small worlds we're only beginning to notice. But here's a question. Do we need to find all of them? Does it matter if there are 600 moons or 6,000? What do we gain by cataloging every rock in Jupiter's orbit? Some scientists would say yes. Every moon is data. Every orbit is a clue to how the solar system formed, how it evolved, how it continues to change. The more moons we find, the better we understand the gravitational dynamics of the Jovian system, the patterns of capture, the rates of collision, the distribution of sizes. Others would say it's enough to understand the principles, to know that irregular moons exist, to know how they got there, to know what happens to them over time. Cataloging every individual moon is a task for archivists, not explorers. Both perspectives have merit. Science is about understanding principles, but it's also about details. Sometimes the details reveal patterns you wouldn't see otherwise. Sometimes an outlier changes everything. Consider this. What if one of those tiny unnamed moons turns out to be unique? What if it has an unusual composition, or an orbit that defies explanation? Or a surface feature that suggests it came from somewhere far beyond Jupiter? We wouldn't know unless we looked, unless we cataloged, unless we cared enough to check. There's also the philosophical dimension. Finding moons is a way of asserting our presence in the universe, of saying, we see you, we acknowledge you, you exist and that matters. Even if the moon is just a rock, even if no one ever visits it. The act of discovery is an act of recognition, and recognition has value. Some of the irregular moons have beautiful names: Irene, Eupheme, Helike, Euide, names drawn from Greek mythology, goddesses, muses, nymphs. Each name carries a story, a history, a connection to the culture that created it. When we name a moon, we're not just labeling it. We're bringing it into our narrative, making it part of human history. And then there are the unnamed ones, the ones still waiting. S2017 J9, S2018 J4. Strings of letters and numbers, sterile, clinical. They'll get names eventually, assuming someone studies them long enough to justify the effort. But for now, they're anonymous, unknown, wandering through space without identity. Does a moon care if it has a name? Of course not. But we care. Names make things real to us. They make them easier to think about, easier to remember, easier to love. And maybe that's what this is really about. Not the science, though. The science matters. Not the cataloging, though, that has value too. But the love. The quiet, patient love of looking at the sky and finding something new, something no one else has seen, and saying, "You matter. You're part of this. You belong." Jupiter's moons, all 95 of them, belong. The big ones and the small ones. The named and the numbered. The lost and the found. They're all part of the family. All part of the story. And the story isn't finished. It's still being written. One discovery at a time. One image at a time. One night of patient observation at a time. But finding moons is only the beginning. Knowing they exist is different from understanding what they mean. And Jupiter's moons mean something profound. They're not just objects. They're lessons. Lessons about how planets form, how life might emerge, how we as a species fit into the larger cosmos. And those lessons are worth exploring even if they keep us awake long into the night, thinking about oceans beneath ice and the possibility that we're not alone. For most of human history, we thought life required one thing above all else: sunlight, energy from a star. Without it, we assumed nothing could grow, nothing could move, nothing could exist. Life, we believed, was a child of the sun, dependent, tethered, limited to the narrow band of space where starlight was warm enough to keep water liquid. Jupiter's moons proved us wrong, not by showing us life. We haven't found life there, not yet, maybe not ever, but by showing us that the requirements for life are broader than we imagined. That water can stay liquid without sunlight. That energy can come from sources other than stars. That the habitable zone, the region where life might exist, is not a ring around a sun, but a possibility that extends far into the frozen darkness. Europa's ocean exists because of tidal heating, not because of sunlight. Ganymede's ocean, buried even deeper, survives on the same principle. Enceladus, one of Saturn's moons, erupts plumes of water from a subsurface ocean warmed by the same forces. These moons are teaching us that habitability is not about distance from a star. It's about having the right ingredients: water, heat, chemistry, time. And if that's true in our solar system, it might be true elsewhere, around other stars, in other systems. Where moons orbit giant planets far from their suns, warmed not by starlight, but by the relentless pull of gravity. Before we discovered hydrothermal vents on Earth, the idea of life without sunlight seemed impossible. Plants need photosynthesis. Animals eat plants. Everything we thought traced back to the sun. But in 1977, scientists exploring the Galapagos Rift, a volcanic zone deep in the Pacific Ocean, found something that shattered that assumption. Communities of organisms thriving in total darkness, 2 kilometers below the surface. No sunlight, no plants. Just heat from the Earth's core chemicals, from volcanic vents. And life that had adapted to feed on those chemicals instead. Tube worms, giant clams, eyeless shrimp. Bacteria that metabolize hydrogen sulfide, a compound that's toxic to most life. These organisms don't photosynthesize, they chemosynthesize. They build organic molecules from inorganic chemicals using energy from chemical reactions instead of sunlight. It's a completely different strategy, a parallel path. Proof that life is more flexible than we gave it credit for. And if life can exist at Earth's hydrothermal vents, why not Europa's? The conditions are similar: liquid water, heat, dissolved minerals, chemical gradients that could provide energy for metabolism. The main difference is location. Earth's vents are at the bottom of an ocean exposed to the sky. Europa's would be at the bottom of an ocean sealed beneath ice, cut off, isolated, but not impossible. Scientists call this kind of ecosystem a chemosynthetic biosphere, a biosphere that doesn't depend on sunlight. And the discovery of chemosynthetic life on Earth changed the way we think about astrobiology. It expanded the search. It meant we didn't have to look only at planets in the habitable zone. We could look at moons, at subsurface oceans, at places that seem too cold, too dark, too far from their stars to matter. Europa became the poster child for this new way of thinking, a moon that's frozen on the outside but might be teeming with life on the inside, a moon that doesn't need the sun, just gravity, just time, just the right chemistry. But there's a catch. We don't know if life actually exists on Europa. We have no evidence, no biosignatures, no confirmed organic molecules beyond the simple tholins that form from radiation. We have hope, possibility, plausibility, but not proof, and that's important to acknowledge, because the absence of evidence is not evidence of absence. Europa might be sterile, the ocean might be too salty, too acidic, too cold despite the heating, or the chemistry might be wrong, missing some essential ingredient we don't know about yet. Life on Earth required billions of years to emerge. Europa has had time, but time alone isn't enough. You need the right conditions. And we don't know if Europa has them. Still, the possibility is enough to justify the search, because the implications are staggering. If we find life on Europa, even microbial life, it would mean life has arisen independently at least twice in our solar system. And if it happened twice here, it's probably happening elsewhere. Everywhere. The universe we'd learn is not barren. It's alive, full of oceans and organisms and ecosystems we've never imagined. That would change everything. Our sense of place, our sense of uniqueness, our sense of responsibility. If life is common, then destroying it even accidentally becomes a moral issue. Planetary protection. The idea that we should avoid contaminating other worlds with Earth life becomes not just a scientific guideline, but an ethical imperative. NASA takes planetary protection seriously. Spacecraft sent to Europa are sterilized, baked in ovens, irradiated, cleaned with alcohol and ultraviolet light. The goal is to reduce the number of Earth microbes on the spacecraft to near zero. Because if we land on Europa and find life, we need to know it's native, not something we brought with us, not contamination, not a false positive. But sterilization is hard. Life is persistent. Bacteria can survive in vacuum, in radiation, in extreme cold. Some microbes can enter a dormant state, a spore-like form, and remain viable for years, decades, maybe centuries. We do our best. But there's always a risk, a chance that something hitches a ride, survives the journey, wakes up when it touches water. If that happens, if Earth life colonizes Europa, before we even get a chance to study what's there, we'll have committed an irreversible mistake. We'll have erased a second Genesis, destroyed evidence of independent evolution, contaminated the most important scientific discovery in human history. That's why we move slowly, carefully, why we send orbiters before landers, why we study from a distance before we touch. Europa is too important to rush, too fragile to risk, and Europa is not the only candidate. Enceladus, Saturn's sixth largest moon, has active geysers, water plumes erupting from cracks in the ice shooting hundreds of kilometers into space. The Cassini spacecraft flew through those plumes, tasted them, analyzed the chemistry, and found organic molecules, amino acids, the building blocks of proteins, not life, but the ingredients life needs. Enceladus is smaller than Europa. Its ocean is smaller, but it's more accessible. The plumes bring ocean water directly to the surface. You don't have to drill, you just have to catch. Collect samples, bring them back to Earth, analyze them, look for signs of biology. NASA is considering a mission to Enceladus, a spacecraft that would orbit Saturn and fly through the plumes, repeatedly collecting material, searching for biosignatures. It's ambitious, expensive, technically challenging, but doable. And if it finds anything that suggests life, it would be worth it. Titan, Saturn's largest moon, is another possibility. It has lakes, rivers, rain, not water, methane, liquid hydrocarbons flowing across the surface at minus 180 degrees Celsius. It's cold, alien, nothing like Earth, but it's chemically active. Complex organic molecules rain down from the atmosphere. They settle on the surface. They react, slowly, creating larger molecules, more complex structures. Could life exist in liquid methane? On Earth, life requires liquid water. But that might be a bias, a limitation of our imagination. Maybe life can use other solvents, methane, ammonia, something we haven't thought of. Titan is a test case, a laboratory for studying prebiotic chemistry, the chemistry that happens before life begins. And then there's Mars, not a moon but relevant. Mars had water, rivers, lakes, maybe even oceans, billions of years ago, and then it lost them. The atmosphere thinned, the water froze or evaporated, the surface became a desert. But beneath the surface, there might still be liquid water, trapped in pockets, warmed by geothermal heat. And if there's water, there might be life, microbial, dormant, surviving. The point is this: the search for life has expanded. It's no longer limited to Earth-like planets and Earth-like orbits. It includes moons, subsurface oceans, chemosynthetic ecosystems, places that seemed impossible a generation ago. And Jupiter's moons started that shift. They showed us that water is common, that heat doesn't require a star, that the universe is more hospitable than we thought. Not easy, not welcoming, but possible. And possibility is all we need. Here's a thought experiment. Imagine we find life on Europa. Simple life. Single-celled organisms. Bacteria-like creatures living in the dark, feeding on chemicals, reproducing slowly. No intelligence, no technology, just life, doing what life does, surviving, adapting, existing. What do we do next? Do we leave it alone? Study it from a distance, or do we interact land? Sample. Extract organisms for analysis. Bring them back to Earth. Risk contamination in both directions. There's no easy answer. Science demands investigation, understanding. But ethics demands caution, respect. The organisms on Europa, if they exist, didn't ask to be discovered, didn't consent to being studied. They're not human. They might not even be conscious, but they're alive, and that matters. Or is bacterial life morally significant? We kill bacteria on Earth all the time, with soap, with antibiotics, with ultraviolet light. We don't mourn them. We don't consider their perspective. Should Europa's bacteria be different? Maybe. Because they're not just bacteria. They're evidence. Proof that life can emerge independently. That Earth is not unique. That the universe is capable of creating biology in more than one place. Destroying that evidence even accidentally would be a loss. Not just for science, for humanity, for our understanding of what it means to be alive. These are the questions Jupiter's moons force us to ask. Not easy questions, not comfortable questions, but important ones. Because how we answer them will shape the future, will determine how we explore, how we interact with other worlds, how we define our role in the cosmos. Are we observers, collectors, colonizers, stewards? What do we owe to life that's not our own? What do we owe to worlds we didn't make and can't control? Jupiter's moons don't answer these questions, but they ask them loudly, persistently. Every time we point a telescope at Europa, every time we plan a mission, every time we wonder if we're alone. And maybe that's the real lesson, that the search for life is not just about finding it. It's about asking what we'll do when we do, how we'll treat it, how we'll change. Because finding life on another world won't just change science, it will change us, our philosophy, our religion, our sense of responsibility, our future. And Jupiter's moons are preparing us for that moment, teaching us, challenging us, showing us that the universe is bigger, stranger, and more full of possibility than we ever imagined. That life, if it exists out there, might be nothing like us, might not even notice us, might just keep going quietly in the dark, doing what life has always done, enduring, adapting, surviving. We've traveled far through Jupiter's system, across moons of fire and ice, through oceans hidden and orbits chaotic. We've seen the old and the young, the stable and the doomed. But all of these moons and their mysteries point towards something larger, a question that transcends Jupiter itself, a question about meaning, about our place, about what we're searching for in the darkness, and why it matters so deeply that we keep looking even when the answers feel impossibly far away. We've been traveling together through Jupiter's kingdom for a while now. 95 moons, 95 worlds, each one different, each one carrying its own story written in ice rock, sulfur, and time. From Io's volcanic fury to Europa's hidden ocean. From Ganymede's quiet complexity to Callisto's ancient patience. From the captured wanderers tumbling backward through space to the lost moons we saw once and never found again. And now, as we drift toward the end of this journey, it's worth asking, what does it all mean? Why do these distant moons matter? Why should we care about frozen rocks and subsurface oceans 500 million miles away, when we have problems here now on our own world? The answer scientists suggest is perspective. Jupiter's moons give us something we desperately need, a mirror, a way to see ourselves from outside, to understand that Earth, for all its beauty and complexity, is just one solution to the problem of being a world, one answer to the question of what a planet can be. When Galileo looked through his telescope in 1610 and saw 4 points of light moving around Jupiter, he didn't just discover moons. He discovered that the universe was larger than the prevailing wisdom allowed, that not everything circled Earth, that we were not the center. It was a small observation, 4 dots moving in the dark, but it changed everything. It opened a door, and humanity walked through. 415 years later, we're still walking, still discovering, still learning that the universe is stranger, more diverse, more generous, with possibilities than we ever imagined. We thought moons were dead. They're not. We thought life required sunlight. It doesn't. We thought oceans needed atmospheres. They don't. Every assumption we make, the universe finds a way to complicate, to expand, to remind us that our intuitions shaped by living on one world in one solar system are limited. Jupiter's moons are teaching us humility, but not the kind of humility that diminishes, the kind that expands, that says, you are small, yes, but you are part of something vast. You are connected to Io's volcanoes and Europa's ocean and Callisto's ancient craters. You are made of the same atoms, governed by the same physics, driven by the same curiosity. There's a concept in astronomy called the cosmic perspective. The idea that when you look at the universe, really look at it, you see yourself differently. Not as separate, not as special, but as integrated, part of the whole. Your oxygen was forged in a dying star. Your carbon came from supernovae. Your water might have been delivered by comets like the ones that bombard Callisto. You are not just on Earth. You are of the universe, and the universe is in you. Jupiter's moons reinforce that perspective. They show us that the processes that shape worlds, tidal heating differentiation, ocean formation, are universal. They happen here. They happen there. They probably happen on exomoons orbiting planets we'll never visit and galaxies we'll never see. The same laws, the same patterns, the same endless creativity. And that's comforting in a way. To know that we're not alone in our strangeness. That Earth is weird, yes, with its life and its oxygen and its talkative species that builds telescopes. But Io is weird too, and Europa, and Ganymede. Weirdness is the norm, conformity is the exception. We've talked a lot about the search for life, about Europa's ocean and the possibility of organisms swimming in darkness. But even if we never find life on Jupiter's moons, even if they're sterile, they're still valuable. Because they teach us about planetary science, about how moons form, how they evolve, how they interact with their parent planets. And that knowledge helps us understand Earth. Earth has a moon, one moon, large by the standards of rocky planets. It stabilizes our axial tilt, giving us consistent seasons. It creates tides which might have played a role in the emergence of life by creating tidal pools where chemistry could concentrate. Without the moon, Earth would be different. Wobblier, less stable, maybe less hospitable. And our moon is slowly leaving, drifting away at about 3.8 centimeters per year. In a few billion years, it will be too far to stabilize our tilt, too far to create meaningful tides. It will still be there, a companion but distant. Cold, like Callisto. And by studying moons like Callisto moons that are geologically dead, we glimpse Earth's lunar future. Jupiter's moons also help us understand exoplanets. Planets orbiting other stars. We've discovered thousands of them. And many are gas giants like Jupiter, which means they probably have moons. Lots of them. Moons we can't see directly because they're too small, too faint, too far away. But we can infer their existence, and we can predict what they might be like based on what we've learned from Jupiter's system. Some of those exomoons might have oceans, might have tidal heating, might have chemistry complex enough to support life. We call them exomoons, and they're the next frontier, the next place we'll look. But we can't study them in detail yet. Our technology isn't there. So we study Jupiter's moons instead. We use them as analogs, as templates, as guides for what to expect when we finally build telescopes powerful enough to see exomoons directly. And that's the beauty of science. You don't have to visit a place to learn from it. You can study it from afar, measure its light, calculate its orbit, model its interior, build simulations, test hypotheses, and slowly, piece by piece, assemble an understanding. We may never land humans on Europa. The radiation is too intense, the distance too great, the challenges too numerous. But we'll send robots, probes, submarines, machines that can withstand what we cannot. And through those machines, we'll touch Europa's ice, taste its ocean, search for life in waters no human eye will ever see directly. That's not a loss, it's an extension, a way of being present without being there. Our curiosity embodied in metal and silicon traveling where flesh cannot. And when those machines send back data, images, measurements, we'll be there too, in spirit, in intent, in the act of asking, what is this place? What can it teach us? There's a poet named Diane Ackerman who wrote, "We are a way for the cosmos to know itself." She was paraphrasing Carl Sagan, but the idea is the same. We are not separate from the universe. We are the universe localized, a small part of it that has become conscious, aware, curious. And through that curiosity, the universe explores itself. When we study Jupiter's moons, we are the universe studying itself. When we wonder about Europa's ocean, we are the universe wondering about its own possibilities. When we mourn the lost moon, S2003J2, We are the universe caring about its own forgotten pieces. And that's profound, not in a mystical sense, but in a literal one, because it means exploration is not optional, it's intrinsic, built into the fabric of what we are. We are made to wonder, made to search, made to look at the night sky and ask, what's out there and how does it connect to what's in here? Jupiter's moons don't answer all our questions. They raise more than they resolve. And that's perfect, because questions are what keep us moving. If we had all the answers, we'd stop, we'd settle, we'd lose the thing that makes us most human, the refusal to accept mystery as final. So, what have we learned? That moons are not simple, not boring, not dead. That their worlds diverse and dynamic, shaped by forces we're only beginning to understand. That water is everywhere. That heat doesn't require a star. That the ingredients for life are more common than we thought. That the universe is full of places where chemistry might become biology, where oceans might hide beneath ice, where life, if it exists, is doing so in ways we've never imagined. And we've learned that distance is not an obstacle. Not really. We can't touch Europa's ocean, can't walk on Io's lava fields, can't feel Callisto's ancient ice beneath our feet. But we can know them, study them, care about them. And in caring, we connect. Across space, across time, across the void that separates us from everything we love. Have you ever looked at Jupiter through a telescope, even a small one? You can see the bands, the storms, and if the seeing is good, if the air is steady, you can see the moons, 4 bright points. Io, Europa, Ganymede, Callisto, the same 4 Galileo saw, moving, changing position night after night, following their orbits just as they have for billions of years. It's humbling and thrilling to see with your own eyes what Galileo saw, to confirm personally that the universe is real, that the moons are there, that the math works, that we're not making this up. And if you haven't looked, maybe you will. Maybe tonight. Maybe soon. Maybe you'll find a telescope or a pair of binoculars and you'll point them at that bright dot in the sky and you'll see. And in that moment, you'll join a lineage, a chain of people stretching back 4 centuries, all of whom looked up and wondered and saw moons circling a giant planet and realized the universe was bigger than they thought. You'll become part of the story, not just a listener, a participant. Because the story of Jupiter's moons is not finished. It's ongoing. And every person who looks, who wonders, who cares adds to it. We've walked far tonight, through fire and ice, through time and silence, through oceans no one has touched and craters older than memory. We've met moons that scream and moons that whisper, moons that were born here and moons that were stolen, moons we've lost and moons we've yet to find. And what unites them all, what makes them matter, is this: they exist. They are real, they are knowable, and they are waiting, patiently, quietly, for us to arrive, to explore, to understand, to ask the next question. Science is not about having answers, it's about asking better questions. And Jupiter's moons give us some of the best questions we've ever asked. Is there life in Europa's ocean? What broke apart the Ananke group? Why does Io erupt and Callisto stay silent? Where is S2003J2? How many moons are still hiding, waiting to be found? We don't know, not yet, but we will. Or our children will. Or their children. Because the search doesn't end. It evolves. It deepens. Every answer leads to new questions. Every discovery opens new doors. And that's okay. That's beautiful. Because the journey is the point, not the destination. The looking, the wondering, the slow, patient accumulation of knowledge, the building of understanding, one observation at a time, one mission at a time, one sleepless night at a time. Thank you for walking with me through Jupiter's garden of frozen worlds, for listening, for wondering, for letting curiosity lead you into the dark. I hope you found something here. Not just facts, though, there were plenty, but something deeper, a sense of connection, a reminder that you're part of this, that the moons of Jupiter are not separate from your life, but woven into it through the physics you share, the atoms you're made of the questions you ask. And if your eyes grew heavy along the way, if you drifted off and missed a moon or two, that's exactly as it should be. Because these stories are not tests, they're lullabies, whispered truths, soft invitations to rest while the universe keeps spinning, keeps exploring, keeps being beautiful and strange and full of wonders we've only just begun to notice. Sleep well, dream gently. And when you wake, maybe you'll look at Jupiter a little differently, not as a distant planet, but as a home, a family, a system of worlds, each one unique, each one waiting for us to understand it, to care about it, to see it not as an object, but as a place that exists, that matters. That's part of the same cosmos you are. There are more stories to tell, more worlds to visit, more questions to ask, and we'll explore them together when the night is quiet and the stars are bright, and curiosity whispers that it's time to drift again. Until then, rest. The universe isn't going anywhere. It will wait. And so will the moons, circling, enduring, glowing softly in the light of a giant planet 500 million miles from here, but somehow strangely close enough to touch. Good night, sweet dreams, and thank you for letting me share this journey with you.